Most of us have heard about the quotient rule in calculus. It's this formula that appears multiple times whenever we try to differentiate some weird looking function with fractions in it. We are rarely told why it's true. How can geometry chip in between all this? It is when substitution comes to rescue. If we are differentiating u over v with respect to x, we can substitute u over v with a single variable q, to which follows that u equals vq. Interestingly, this seems familiar, doesn't it? How about creating a rectangle with sides v and q so that the area equals to vq? In sense is the case with most portion of calculus, the dv and dq be the infinitesimal changes to the length of respective sides. Now, let us muse at the new development. What is the change in area that our accidents of why not infinitesimal changes caused? If you look at the small rectangle to the right side with sides dq and dv, its area is very small, so it's fine even if you neglect it. So what happens now? The change in area du is pretty much equal to the sum of area of rectangles in our left side, q dv plus v dq. Remember, we substituted q for u over v, so it's time to put back the value of q. Let us not hurry to put the value of dq for a while, we'll deal with it later. After some mundane algebraic manipulations, we first try to bring dq on one side and divide by dx on both sides. We're ready to substitute q in dq, and that's the final ring. So there you have the quotient rule just from geometry and some infinitesimal changes. It kind of makes me chuckle how mathematics is full of connections.